Hello. In this lecture, we are going to discuss about types of chemical reactions. So I'm going to start with the very first one that is called as combination reaction. Then we have decomposition reaction. So first we are just going to view how many different types of chemical reactions that we are going to study in this lecture. Then one by one we are going to take some examples for the same. Then we have displacement reactions. Then we have based on energy, exothermic and endothermic reactions. Then we have another one that is called as double displacement reaction. So under this, we have different types of reactions for combination, decomposition, displacement. We have for double displacement also, and for decomposition reaction also. Then the last one is going to be redox reactions. So if we talk about combination reaction, we have further three classifications for combination. One is element and element combination. Then we have element and compound and compound combination. E stand for element and C stands for compound. Under decomposition, we have thermal, we have electrolytic, we have photolytic or photochemical also. So under displacement, we are going to study only for metals and non-metals. For double displacement reactions, we have precipitation reaction. That's a type of double displacement reaction. And the second one is neutralization reaction. So we are going to discuss one by one in depth of all these chemical reactions. So we are going to start with combination reactions. So from the term itself, combination meaning something that we need to combine. So we already know that reactants are written on the left hand side of the arrow, and on the right hand side we have our products. We already know that. So if we have any two reactants, let's say A and B, they are going to combine together to give a single product. So that's the identity of a combination reaction. So we can say these chemical reactions involve the combination of two or more substances to form a single product. So that's the identity of combination reaction. Because we do have, which we are going to discuss in a couple of minutes, decomposition reaction, which is very much opposite to combination reaction. So, as I have told before, combination reactions can be of three types. It can be element element, it can be element and compound. So, it can be compound combination, but in all these three, one common thing is that they will combine to give us a single product. So, it's the product is always going to be a compound, or it can be a molecule of different elements. So, first we are going to discuss is combination reactions involving two elements. And specifically, this combination reaction is also called as synthesis reaction. Synthesis is a term when we synthesize some compound from its respective elements. So, the only combination reaction where two elements are going to combine to give us a single product, that is synthesis reaction. So we can call it as redox reaction. You'll understand later how we can call this as a redox. We can even call it as a combination reaction. We can call it as synthesis reaction. So the out of three classification of combination, this is the only synthesis reaction because it's made from its respective elements. So magnesium oxide is made from its magnesium and oxygen elements over here. So this reaction we have already discussed before. So magnesium in the solid state, oxygen in the gaseous state, magnesium oxide solid. So we need to balance it. So over here we can put the coefficient. Another example that we can take is this reaction Haber's process, which we discussed before. It's a reversible reaction. This is also combination reaction. So we can balance it. All are in the gaseous state. I'm not going to write the reaction conditions as of now, it's not required over here. Then the simple reaction which we see in most of the common books and various places, any form of carbon. It can be charcoal, it can be any variety of coal. It reacts with oxygen and gives us carbon dioxide. So it's a perfectly balanced equation, we don't need to balance it. So this we need to remember that any two elements combine to form a single new compound. These are combination, and these specific combination reactions are called as synthesis reaction. That's a very important point. Then the next that we have is combination reactions involving an element and a compound. So we need to think in a way where we need to take only one element and the second reactant can be a compound or it can be a molecule. So we can use this reaction, nitric oxide reacting with oxygen to give us nitrogen dioxide. Now, this nitric oxide is very much neutral in state. When we say non-metallic oxides, non-metal and oxygen together, so we say this nitric oxide, non-metal and oxygen together, if it's a neutral, that means if you add it in water, if you diffuse this particular gas in water, it will not change into acid. Most of the non-metallic oxides are acidic in nature, metal oxides are basic in nature. Then some of the metal oxides are amphoteric, and some of the non-metallic oxides are neutral also. That in depth, these terms we'll be studying in acid basis salts. So, nitric oxide is in the gaseous form. We have oxygen in the gaseous form, and we're getting nitrogen dioxide, which is again another gas. Since it's a chemical reaction, but there is no change in physical state. So, next that we can balance this. So we have three oxygen atom on the left hand side, two on the right hand side. So if we, the minimum number, the minimum coefficient that we're going to add in front of nitrogen on both sides is 2. So then we just have to see if oxygen is getting balanced on both sides. So we have total 4 oxygen over here, 2 and 2, 4, and 2 oxygen over here and 2 over here. So sum it up, total 4 oxygen on the left hand side, right hand side also 4 oxygen. So this is balanced now. And this is another oxide of nitrogen. We call it as nitrogen dioxide. And please do remember, wherever you produce or wherever you find nitrogen dioxide, it has a property of showing brown fumes. Nitrogen dioxide, wherever formed, it will always be brown fumes. Otherwise, nitric oxide is colorless, but this is colored gas. Then, next, combination reactions involving two compounds. So over here we can take multiple reactions. There can be n number of examples. The same example which we took in the previous lecture. So ammonia reacting with HCl forming ammonium chloride. So this is in the gaseous form, this is in the gaseous form. We are not taking aqueous form of HCl over here. So it's a perfectly balanced equation. So ammonia and HCl they're molecules, but they're made from different elements. So we can take this kind of example, two compounds or molecules. Another example that we can take over here is calcium oxide reacting with water. So calcium oxide is solid in state. This is also called as quicklime, we have discussed before. So reacting with water will give us calcium hydroxide, which is in the aqueous state. So this calcium hydroxide, previously we discussed, this is also called as slake lime solution or lime water. Otherwise, in chemical name, we call it as calcium hydroxide. So this reaction is also called as slaking of lime. Why do we say like that? For us, lime is this. Commonly, we call calcium oxide as quicklime or simply lime. So you converted this calcium oxide into slaked lime, that is lime water, calcium hydroxide. So slaking of lime, that's why we are calling this particular reaction. And this can happen at perfectly room temperature. Next that we're going to discuss is the decomposition reactions. From the term itself, decompose, breakdown, breakdown of some complex, or you can say not complex, but any kind of compound into simpler one. So we are going to decompose. No doubt, decomposition can happen of the, you can say, any kind of decaying of any kind of organic waste is decomposition that is happening for the complex organic matter over there. So it can be there, but we are going to study only simple reactions under decomposition reactions. So how we can define it? So if we have another compound, any kind of compound or molecule, it's breaking up into its components. So we can say this particular reaction is quite opposite to combination reactions. So if we get multiple types of reaction in a question, and if they are asking us to identify the type of reaction, so decomposition and combination are very easy to identify. Combination, where two reactants are combining to give a single product, that's identity. Decomposition, a single compound or a molecule is going to break up into its respective elements. That's the identity of decomposition reaction. So how we can define it? We can define it like this: conversion of a single compound into two or more simple molecules or substances. That is called as decomposition. So, the various types of decomposition reactions that we're going to discuss as of now. So, we have the very first one, thermal decomposition reaction. So, we can say this is decomposition in the presence of heat. So, we are going to take certain examples for this type of decomposition reactions where heat is required. So there are multiple. We have this reaction, calcium carbonate. If you heat it, so this is delta sign. For any kind of heat change, we use delta sign over here. So if it's in the solid state, if the this calcium carbonate is in the solid state, that will decompose to give us calcium oxide, another solid state, and carbon dioxide. So we are following the rule. We have a single compound breaking up itself into multiple products. You can see that. So this is one thermal decomposition reaction. We can take multiple examples. There are many examples under this. So we can use this particular salt. This is called as commonly green vitriol. That's green in color. Or we can even write it like this. Ferrous sulfate. Heptahydrate. So vitriol stands for the seven molecules water of crystallization which are bonded to one unit of FeSO4 over here, ferrous sulfate. So if we heat it, initially it will give us FeSO4, ferrous sulfate, and the water of crystallization will be removed, seven molecules of water. But if we continue heating further, this ferrous sulfate can decompose into Fe2O3, sulfur dioxide, and sulfur trioxide gases. This is this is in the solid state, and this is also in the solid state. This is liquid because it's water. This is solid state, ferrous sulfate, Fe2O3 is also in the solid state. Now the sulfur dioxide and the sulfur trioxide are in the gaseous form. So we need to balance this. If we put 2 in front of FeSO4, because on the right hand side you can see there are two iron atoms, so iron is balanced. Now we have sulfur 2 atoms, one atom over here, another over here, adds up to 2. 4 into 2 oxygen atoms, 8 on the left hand side. On the right hand side we have 3, 4, 5, 6, 7, 8. So total, if you sum it up, all the oxygen, it's 8. So it's a perfectly balanced equation, like just by adding 2 coefficient in front of FeSO4. And this reaction, this is colorless. Just remember the color, green color is going to disappear if we are going to heat because the water has been removed. Most of the time, the salts that we study, the color that they are imparting, it's because of the presence of water. It's not like if they are not having water of crystallization or water molecules bonded over there, so they will not show color. They can be colored in their own state also, but most of the salts, the you can say the kind of salts where this water of crystallization we call it, so it's there. So if it's colored, so if you heat it and there is removal of water of crystallization, so generally they become colorless. Now, in this particular reaction, we have something called as burning smell of sulfur. Now, when we say burning, burning means irritating to the nose. It's like like ammonia also has some pungent smell. right? So there is some irritating, you can say, smell which causes burning sensation to our nose. That is the burning smell of sulfur. So we should not definitely, but it causes irritation to our nose. That is one property of sulfur dioxide and sulfur trioxide. Then another example that we can take over here is lead nitrate, PbNO3 whole twice. Lead over here with the charge 2, nitrate. So this is very much white in color. This is a white color salt. If we heat it, we are going to get PbO, which is lead monoxide. Lead over here, the charge is still 2, and this is very much yellow in color. Now the lead nitrate that we have taken is solid in state. Lead monoxide is also solid, and we are going to get two gases. One is nitrogen dioxide and another is oxygen gas. Now, how we can remember it? We can just write metal nitrate. If we heat it, we will get metal oxide plus NO2 plus oxygen. So we cannot say that every metal nitrate is going to show this kind of reaction, but most of them do so. So what we can remember that if we have most of the nitrates, if we say nitrates, not any other radical, nitrite and nitride I'm talking about only nitrates. So most of the nitrates, when they decompose, they will give you metal oxide, the respective metal oxide. And since it's nitrate, so we are going to get NO2 out of it and oxygen. So oxygen, we know that it's a colorless gas. And NO2 we just discussed, this is brown fumes. Now we need to balance this. So we have we can do it in the fractional way also. If we want, we can do in the whole number coefficient system also. So we can do in both ways. So if we don't want to increase the number of moles of lead nitrate, if we want to keep it as just one, so we discussed that before also, we can actually put a fraction for at least this oxygen, because uh, this we can lead is balanced, one atom on both sides. Nitrogen, we have two atoms, if you can see this one, so we can put two nitrogen over here. And then we come to this oxygen. So 3 into 2, 6 oxygen atoms. So we have 4 in NO2 over here, you can see, plus 1 5, and then add it up to 2, 7 are there. So how to make it 6? So what we can do, we can just put half over here. So we discussed that before, this half and this 2 will get cancelled. So we this half O2 stands for one oxygen atom, then 4 over here, 5 total, then 1 6. So it's perfectly balanced. Or if you want to, we don't like this, if you don't like the fractional part, we can actually write, multiply this entire equation with 2. Like you put 2 over here, this will become 2, this will become 4, and this will remain 1. So this is 2 PbNO3 whole twice, 2 PbO plus 4NO2 plus O2. So this is also balanced. This is also correct. This is also correct. Both are fine. Then we can take one more example. Mercuric oxide. Or we can even write like this. Mercury with a charge that is 2, oxide. So if we heat it, we will get mercury, which is in the liquid state. Mercury 2 oxide is solid, and we will get oxygen in the gaseous form. So again, if you want the fraction, we can put half over here, but if you don't want, we can actually put double this. The lower number that we have is 2 only, so this will become 2, and oxygen is balanced. So This is balanced equation. Or we can write like this: half O2. This is also perfectly balanced. Both are correct. Now we move to electrolytic decomposition reaction. We are done with the thermal. There are many examples. You can go through any source, any different books for studying this chemical reactions and equations. You can find n number of examples in different kind of books online. You can find any source. There is no end to it. So we can just do certain examples and we have to remember it. Now, please remember chemistry is very much practical, but we have to give a theoretical exam for the same sometimes along with the practical also. So in that case we need to remember what we did in the practical part. So all these chemical reactions what we are writing are a part of practical setup, practical labs we have. It's all based on experiments, so we can't just hypothetically write an equation and prove it to be correct. We can't do that. So it need to have some experimental evidence behind. So the tough part is to memorize all this when you're going to write the theoretical paper, the theory paper for your exams, and that is tough. That's tough, but it's not impossible. If you really want to do something, if you like this subject, definitely you will be able to grasp that with proper learning and with proper conceptual building. Chemistry is all about understanding. You cannot just mug it up. You will definitely forget something out of it if you haven't understood it properly. Then we go to electrolytic decomposition reaction. From the term electrolytic, what can come to our mind? That means electricity is involved. So this decomposition reaction, you can say, is caused by electric current taking place in the presence of electric current. And we even call this as electrolysis. Electrolysis is decomposition reaction happening in the presence of electric current. So we can even call it as electrolysis. Now we're going to take some few examples. So first one, the common one, water decomposition. So in the presence of electric current. Now please remember, most of the time we have heard the statement that water is a poor conductor of electric current. That is true. We are talking about pure water, we are talking about distilled water. We are not talking about tap water. Tap water can conduct electric current because it has a lot of ions in it. So, and one more thing, if we are standing in a lab, we are definitely going to use distilled water. We are not going to use tap water. So the water that we have taken over here is definitely distilled. So how can you give electric current to it and it can just decompose into hydrogen and oxygen just like that? It's not that simple. You have to add some few drops of concentrated sulfuric acid just to increase the conductivity. So what this particular, you can say, few drops of sulfuric acid is doing, so this is added to increase the conductivity of water, because water is a poor conductor of electric current. So until unless we don't add this, it's a sulfuric acid, specifically the concentrated one, is a very good electrolyte. Now what the hell is electrolyte? Electrolytes are chemical substances which can conduct electric current. They can be good, they can be bad, but definitely electrolytes' job is to help something conduct electric current. If that something is a poor conductor, just like we have our water over here. So hydrogen gas and oxygen gas that we are getting over here. So if we need to balance it, again you can use a fraction on the theoretical grounds. We can use that have fraction for the oxygen over here. But if you want to increase the moles of water, we can just put 2. And this will be also 2 because hydrogen total atoms, if you see over here, 2 into 2 is 4 and this is 4. And oxygen is already balanced because it has 2 oxygen atom on the right hand side, and over here also we have this 2. This 2 is indicating 4 atoms of hydrogen, 2 atoms of oxygen, like that. Now in this example, that's a very typical question we get. So what volume of gases are deposited on both electrodes? So when we say electrodes, we are talking about cathode. Cathode is a, you can say, electrode or the potential carrying negative charge. And then we have anode, which is carrying positive charge. So you can remember, like, cations being positively charged will be moving towards cathode. So obviously the gas which is going to be deposited over here is going to be hydrogen gas, and at anode oxygen, because oxygen forms anions, this form cations. So this is at cathode, this is at anode, but they are asking this, what volume of gases? They are not asking which gases. What volume of gases are deposited on both electrodes? So if you remember from the previous lectures, we did Lusak's law. So these you can say coefficients can be taken as simple whole number volume ratio. It's not only for gases, because it's actually for only gases only, but over here we have taken water in the form of liquid. That's okay, that's perfectly fine. But this water is going to change into the vapor form first in the presence of electric current, and then change into gaseous forms like this. So we can consider that Lusak's law over here. So what volume of gases? We have to use these coefficients in the simple whole number ratio. So if you see hydrogen, it will be, answer will be 2 volume of hydrogen are deposited on cathode, and for oxygen it is 1 volume. And how many volume of water we are taking? That is 2 volume. So if we simplify it, if it's going to be 1 volume, then this hydrogen gas will also be 1 volume, but oxygen will be half volume. I just reduced it. So moving ahead to the next example, that is NaCl, sodium chloride. That's a molten form. Molten means you have heated it, you have added some few, you can say 1 or 2 drops just to make it a paste of NaCl. Molten is very similar to what we see as a lava. So if you give electric current to NaCl, so what we will get? We will get sodium and we will get chlorine gas. Sodium is deposited as in the form of, you can say, solid. And again, you can put half over here just to balance this equation. But if we don't want to, we can actually put perfectly, we can balance this. So sodium form cation, so this will be deposited at cathode. Chlorine form anion, so this will be deposited at anode. So this should be very much clear in mind, what goes to cathode, what goes to anode. So we are not into very high levels of, you can say, this electrochemistry part. We are just discussing the very basic electrolysis part. We know cations move towards cathode, anions move towards anode. So we can actually do that in a, you can say, in a diagram. So if we have these electrodes connected to a battery, and this is the electrolyte. So electrolyte is a solution which is going to supply the ions to, this is to the electrode, this is cathode, the negatively charged potential, and this is anode, the positively charged potential. So one thing, we are going to take these electrodes, the material that we are going to use over here are going to be inert electrodes. Inert in the sense they can be platinum, it can be carbon, it can be graphite, anything, but it's never going to be reactive electrodes. The reactive electrodes can be made from certain metals which are reactive. Definitely not platinum is not reactive, it's a noble metal. So this is how you can say we if we have taken the electrolyte like water with few drops of sulfuric acid, to be more precise concentrated sulfuric acid. So we know hydrogen will be starting depositing at cathode and over here oxygen. So how do we know in practical, if you see the practical demonstration of this entire experiment, you will be able to see some bubbles around these electrodes. So if there are bubbles that you will be able to see, that confirms the experiment that we our experiment is running at the first place. But if you don't see the bubbles, so there is a possibility it is not happening, the whole reaction is not happening, or there is some other problem, we didn't connect the circuit properly, we did something wrong which is not, completing the whole particular reaction. Next that we are going to discuss is photo decomposition reaction. We can even call it as photochemical reaction, photolytic decomposition reaction. There can be many names. So this decomposition reaction is caused by light, photons. That's why the term photo. So we can take this example, AgCl, AgBr. These are both white color salts. So if we are in the presence of sunlight, it will give you silver and chlorine gas is released. So we can balance this. This is solid, and chlorine is in the gaseous form. So this is silver color. And these both salts are very much white in color, and these can be very much used in black and white photography. So this is silver bromide, and this is silver chloride. Both are insoluble in water. So this will again give us silver and bromine. Bromine is in the form of vapors. So both can be used as, you can say, in black and white photography. Then we can take another example, that is hydrogen peroxide. So in the presence of sunlight, it will decompose into water and oxygen. Now we have a story related to this hydrogen peroxide. It's not the historical story I'm talking about. So hydrogen peroxide is very much, you can say, similar to water. It's viscous liquid. Viscous means it has slightly high density, but it looks like water. So there's if we try to pour it to another beaker, so we can get to know that this is not exactly water, but it looks like transparent water only. It's slightly thick. That's why the term viscous. Viscous means viscosity means resistance to flow. Now this hydrogen peroxide, it has a shelf life. In certain days it can change into water and oxygen. Water in the form of liquid, oxygen gas. Now that's why we try to store hydrogen peroxide in dark colored bottles, specifically brown color bottles, and we try to store it in a cupboard where even the white light or any tube light, artificial light, sunlight is not able to approach, because there is a possibility hydrogen peroxide will decompose into water, and we have to make it fresh after certain days because we can't use the old one. There is a possibility it might have changed into into water completely. So if we need hydrogen peroxide in any experiment and if we don't make it fresh, we can use it for a couple of days, that's not a problem. But if we don't make it fresh and we're using quite, you can say, old one, maybe 4 5 days old, or even multiple weeks have passed, so that there's a possibility it might have changed into this water. So so that's why we this can be a good question, that why hydrogen peroxide is stored in dark colored bottles. So the reason we know, because in the presence of sunlight, it will decompose into water and oxygen gas. So coming to the balancing part. So again we can use half over here. This will be perfectly balanced equation, but if we don't like this half, we don't like the fraction 1, so we can use a coefficient in front of hydrogen peroxide, then you have to use in front of water also. And now if you see, this is perfectly balanced. So we have total oxygen 4 atoms, so 2 over here, 2 over here, hydrogen is balanced, everything is balanced. Then we go to another example. This is hypochlorous acid. If you remember the part from the radicals, so ClO minus is hypochlorite. So if you add hydrogen to it, it will become acid. So it's a type of oxyacid. Oxyacids are those which are having a non-metal, this non-metal, and there is a hydrogen and oxygen. Usually any kind of acid will always have hydrogen and non-metal for sure. But if you have additionally oxygen, so we call it as oxyacid. Similarly, we have something called as hydroacids. HCl is a hydroacid, hydrochloric acid, because it has a non-metal and hydrogen. Again, this part we'll be discussing in acid basis salts, but there's no harm having a, you can say, single statement that can stay in your mind for longer duration of time. So the next time if I discuss about hypochlorous acid, you will remember it. So this we have to take aqueous because it's an acid. It has to be aqueous. In the presence of sunlight, this will decompose into hydrochloric acid and oxygen gas. So this is also aqueous. So hypochlorous acid decomposes to give hydrochloric acid and oxygen, right?